Good afternoon. Thank you all for being here, and for those in the room, and also for those joining us online. We're here to honor the legacy of one of the very great scientists of our university, and to continue that search for understanding that he devoted his life to. Welcome to the Steve Weinberg Memorial Lecture. I want to recognize a special guest who's with us online, Louise Weinberg. She is a professor emeritus of our university and holds the position of the William B. Bates Chair in the Administration of Justice at our School of Law. We are grateful for her years of teaching and scholarship, and we're also grateful that she brought Steven to the 40 acres. They enjoyed more than 65 years of marriage, and she established this lecture in his memory. Steven Weinberg was one of the greatest physicists of the 20th century. He transformed our understanding of the universe into fundamental laws that govern it. In 1979, he won the Nobel Prize in Physics. He discovered new ideas by asking great questions. He believed, as he once said, the progress of science has been largely a matter of discovering what questions should be asked. We're grateful that he brought his work here in 1982, spent nearly 4 decades building something truly special at UT Austin. He gathered remarkable minds, trained generations of physicists, and made this university a thriving place for scientific inquiry. Stephen had a gift for sharing scientific knowledge with the world. He presented to public audiences, he wrote popular science books, but he could connect physics to poetry, science to humanities in ways that invited others into those questions. He reminds us that the desire to understand our world is something that we all share as humans. Steven Weinberg knew that there was always more to discover and more to share. That's why every 2 years, we bring together great scientists to this campus to share his or her work. Today's speaker, Dr. Vicky Kalogera of Northwestern University, will present today. But it's now my great privilege to turn this conversation over to David Vanderbout, Dean of the College of Natural Sciences. To tell us more about her outstanding work, please welcome Dean Vanderbout.
All right, thank you, President Davis, and good afternoon. It is my great pleasure to introduce our speaker for the 2026 Weinberg Memorial Lecture. Tonight, we have the opportunity to hear from a leading astrophysicist, globally recognized for her pioneering work on compact objects, black holes, neutron stars, and white dwarfs, as well as for her leadership in gravitational-wave astrophysics. Vicky Kalogera is the Daniel I. Linzer Distinguished University Professor in the Department of Physics and Astronomy at Northwestern University. She earned her BS in Physics from the University of Thessaloniki in Greece and her PhD in Astronomy from the University of Illinois at Urbana-Champaign. She completed a postdoctoral fellowship at the Harvard Smithsonian Center for Astrophysics. As the co-founder and director of the Center for Interdisciplinary Exploration and Research in Astrophysics, Sierra, Dr. Kalogera fosters collaborations across astrophysics, data science, and computation. She also directs the NSF Simons AI Institute for the Sky at Northwestern, one of 2 such institutes in the country that developed advanced AI tools for astronomy. The other is here, if you didn't know, so we're extra glad to make that connection. Dr. Kalogera is a key member of the LIGO scientific collaboration and contributed to the first detection of gravitational waves in 2015. Her research bridges stellar evolution, gravitational wave sources, data-driven astrophysics, integrating machine learning, and high-performance computing. Her scientific achievements have been widely recognized, including with the Guggenheim Fellowship and through collaborative honors, among them a special Breakthrough Prize in Fundamental Physics and the Bruno Rossi Prize. She is an elected member of the National Academy of Sciences and the American Academy of Arts and Sciences. She's a fellow of the American Physical Society, the American Astronomical Society, and the AAAS. So please join me in welcoming this evening's esteemed speaker, Dr. Vicky Kalogera.
President Davis, Dean Vandenbout, thank you. Thank you to the whole community and to my hosts at the Weinberg Institute. It's a really a distinct honor to be invited as your lecturer in this series. Steven Weinberg has been one of the towering figures in our field, in physics, in cosmology and gravitation. And I feel quite fortunate to have had a professional path that brings me to this moment. Given where I come from, originally growing up in a small town in Greece, this was not going to be my path, let me tell you. So I am both grateful, humbled, and honored. So it's a pleasure to be here. I had a great day, all day. I met students, postdocs, of course, faculty, colleagues, and friends, and I'm looking forward to the lecture now. So before I get to my topic of discussion, I realized I found out recently that Steven Weinberg, of course, contributed tremendously in gravitation and cosmology, but actually he also got interested in astrophysics and specifically stars and binary stars towards the end of his life. And I also figured out that not everybody, even here, knew that. So I thought I would highlight the fact that in 2020, a book of lectures on astrophysics was published by him, written by him. And I don't have a photograph of the contents, but the first chapter is stars, and the second chapter is binary stars, and this is partly what we will, and compact objects, and this is partly what we will be talking about today. So it's a distinct pleasure, as I said. All right, so let's get going. So what I'm gonna tell you about today is cosmic collisions that were discovered, were hypothesized for a long time, and some sources of these cosmic collisions were known already through other means of observations. But in 2015, we made the first discovery that opened up a completely new field of allowing us to study the universe in a new messenger, in a messenger that we call gravitational waves. So we're going to talk about gravitational waves. We're going to talk about black holes, neutron stars, and where we are 10 years later. So the discovery happened in September 2015, but we announced it to the world after a lot of study in February 2016. And just a few months ago, we were celebrating 10 years of this new field. Again, it has been a privilege of mine to have been at the forefront of this discovery as a member of the LIGO collaboration at the time, along with several of the faculty here in Austin, at UT Austin, my colleagues and my friends working all together to open this field. All right, so let me see if this is going to work out, because we didn't test the sound. So here's how we all heard the announcement of the discovery. Now I stressed you, right?
You just need to plug it in.
Do I have a... I have the MacBook Air. Do I have that? Oh, okay. Oh, I do. Okay.
Just wait. Plug it back.
So before we listen, this is on February 11th, 2016. at the National Press Club in Washington, D.C. This is Franz Cordova, an astronomer, at the time director of the National Science Foundation, Gabby Gonzalez, the spokeswoman of our LIGO scientific collaboration, Ray Weiss and Kip Thorne, two people I would proudly call fathers of our field of gravitational wave physics and astronomy, who later received the Nobel Prize for this discovery, and Dave Reitze, a proud Northwestern alum, who was and is the director of the LIGO lab. And on that day,
ladies and gentlemen, we have detected gravitational waves. We did it.
Many other things were said that day, but this we call Dave's mic drop moment. And there is a story behind, but all I will say is that that was not what he was supposed to say. But the rehearsals before the press conference were not going well. He was supposed to say something more eloquent and well planned by the press people. And because the rehearsals were not going well, he kind of used an expletive at some point, and he said, "I'll just talk the way I talk." And he got up and he said this. We did it. Because this was an effort over 40 years. But what was it that we actually detected? Well, we knew that what we detected was actually the collision of two black holes coming in a nice dance, close and closer together, until the two black holes, who don't really have a surface, but we think of them as having a surface, touched and became a distorted single object. And through this dance, they were disturbing the space-time around them and emitting gravitational waves, the purple layers and rings that you see here. When the black hole, the unified black hole that was formed at the end of this collision, settled into a nice spherical object, then the waves stopped being emitted. We're going to come back to how the waves are being formed and why, etc. But the point is that this is a catastrophic cosmic event. It's not some kind of an event that continues to emit radiation or waves forever. It's not like our sun. Instead, the two black holes are doing their dance, emitting gravitational waves, and at some point there is an end. So going back again to the movie, what the detectors detected was actually this little oscillation. We're going to talk about how little was. And the closer the black holes came, the oscillation became of higher and higher frequency, the peaks coming closer and closer together, and of higher and higher amplitude, because the disturbance of the space-time was stronger and stronger. Okay? So what you see here at the bottom is actually a simulation that solves the equations of Einstein's theory of general relativity and predicts the kind of signal LIGO was meant to detect. And we're going to make visual comparisons between this prediction of Einstein's theory of general relativity to the data that the LIGO detector connected, but we're going to take it step by step. I'm just giving you sort of the punchline in the beginning. Now, I should say, solving Einstein's equations on computers and doing these simulations was far from trivial. Some of the pioneers of this effort are here in this room, like Professor Matzner, and also following Professor Matzner, Professor Laguna and Deirdre Shoemaker, if I don't get it wrong. So it's amazing to be, again, in this place, the space of Steven Weinberg, but also my colleagues who really pioneered this field. Okay, so let's get moving. I told you that the discovery was done by gravitational wave detectors called LIGO. LIGO stands for I need the laser pointer. LIGO stands for Laser Interferometer Gravitational Wave Observatory. And we have 2 such telescopes to detect gravitational waves, one in Louisiana and one in Washington State. They kind of look similar, and they look nothing like a traditional telescope, as you can tell. So L-shaped tubes, these are vacuum tubes, and we're gonna go into a little bit more detail about what's going on into these vacuum tubes and why we need them, etc. But now, soon after LIGO started observations, and we had a couple first few detections, a third detector has joined the field. It's called Virgo, and it is the European gravitational wave detector in Italy. So now we work as a global international network, and we analyze data for our discoveries. So these detectors, to make that detection, they're measuring the oscillations, the disturbances in space-time that are tiny. They're nothing like what you see on your screen, okay? They are changing space, let's stick to space, it's easier, by only 1 part in 10 to the 21. We're gonna come back to this number and what it really means. Because, you know, even to the scientists, what does it really mean, okay? It's hard to fathom. This was and is still the most precise measurement made by humans across of all science and engineering. It was a major feat. The fact that this took decades to become reality and the detection to be achieved is not because it was easy. Most people made fun of the pioneers, said it will never happen, it's impossible, and we'll never have an actual detection, and this will never be an astrophysics field. That was the prediction when I joined the collaboration in the late 90s as a postdoc. Where are we now? 10 years later, okay, 2016, we announced 1 black hole collision in that spiral dance. 10 years later, this is where we are. I'll describe a little bit what you're looking at, but we have more than 200 black hole collisions detected, and we also have neutron star collisions detected as well. So again, I'm now giving you the present punchline. What you're looking at is, in blue, the collisions of gravitational waves. In orange, the collisions of, black hole collisions, neutron star collisions, also gravitational waves. But we knew of the existence of black holes and neutron stars in electromagnetic waves before this discovery. So we're marking those as well. In what measure? What we're plotting on the vertical axis, we're plotting the mass, how heavy, how massive are these compact objects. And then I'll explain that, of course, every collision involves 3 masses. The masses of the 2 black holes that are coming together, and the mass of the final black hole that is formed at the end. The final black hole mass is not equal to the sum of the 2 black holes coming together, because we're losing energy in the gravitational waves, and energy, according to Einstein, is mass, EMC squared. So I hope this is not my phone, and it's okay if it's somebody else's. So the waves are being emitted for us to detect, and the pair of masses is losing energy, but it's really losing mass. So the sum of the final mass is not the sum of these 2 masses. So for each vertical line here, what you see is the mass of 1 black hole, the other black hole coming together, forming the 3rd black hole, okay? All right, so a few things to notice. And the x-axis, we always have to describe our axis when we show plots, as we tell our students. The x-axis means nothing, okay? So It's just placement of all our sources so we can see them in a nice shape. In fact, if you Google massive stellar graveyard Northwestern, you're going to find a web sort of thingy that you can manipulate and arrange these discoveries in any way you want. Okay? So I like the butterfly shape, and this is what I'm showing you. All right, so a few things to notice. The black holes we knew from electromagnetic waves, they were as massive as maybe 20s or 30s solar masses. The black holes, first of all, a lot more black holes we have discovered, so we're learning a lot more about black holes. But also, we're discovering much more massive black holes that exist in the universe of the stellar mass scale. I'm not talking about black holes, if anybody has heard. I'm not talking about black holes in the centers of galaxies of millions and billions of solar masses. Those are not coming from stars. So we found black holes more massive. We found them in much larger numbers that allows us to ask science questions we couldn't ask before. And then we found neutron stars in orange. And then we found objects somewhere in the boundary between the two that are doubly colored because we cannot tell from gravitational waves if they are neutron stars or black holes. Those are our mystery objects for now. So lots of questions have opened up. All right, now we're going to take a step back. What are black holes? What are neutron stars? What is Einstein's theory of general relativity? What are gravitational waves? What brought us here? At the end, you're going to pick up a piece of paper and you're going to pass the test. If you don't pass the test, you cannot leave the room. I'm joking, of course. All right, so in one sentence, the kinds of black holes I'm talking about, and neutron stars, are formed from stars. Now, our star, all stars are formed from gas and dust nebulae, and typical stars are like our sun. And that's the last time I'll mention our sun, because our sun is going to go through its evolution. At some point, it's going to die and form something we don't care about for tonight. It's going to form a white dwarf that doesn't enter the LIGO picture. But it's a compact object as well, by our definitions. Massive stars, more massive than about 10 times the mass of the sun, they also go through their lifetime of nuclear burning in the center, and eventually they also die, but they die with a big splash. They announce to the whole world they're dying, most of them. And they form either a neutron star or a black hole. Okay? So compact objects are basically corpses. Okay? I'm dealing with dead remnants. Your colleagues, many of your colleagues in the physics department here, not in the whole physics department, but in the gravitation part of the Weinberg Institute, they're dealing with corpses. All right, to give you a sense of why we call them compact objects. The last time I showed this, I was in New York City. So I showed Manhattan. Normally, I show Chicago. So comparison. A metropolitan city area is what it is in terms of size. And to scale, a neutron star of about 1.5 times the mass of the sun has a radius of about 10 kilometers. Okay? Somebody told me is running a race this weekend of 10 kilometers. So you're going to run the radius of a neutron star. Okay? And this is the size compared to Manhattan, to scale. A black hole, same mass, more compact, about roughly half the radius. Okay? So they're tiny. Think about this. The whole mass of the sun in 5 to 10 kilometers, or twice that is the diameter. That's why they're compact objects. They have very weird properties. All right, now, Einstein's theory of gravity. Normally, we experience gravity the way Newton described it, okay? And in Newton's theory of gravity, there are no gravitational waves. So our experience is more aligned with this picture. We have two masses. I don't know why they're yellow or blue, but this is how our past student, Carlos Rodriguez, drew them how. So, and the understanding in Newton's era, and until Einstein, was that any two masses are coupled by some rod, not physical rod, but some power that instantaneously acts between the two masses. And if you kick one mass, let's say the light mass around the heavy mass, perpendicular, then it's going to go around the circle, like the Earth is going around the sun, okay? That was the picture. However, and masses move, but space and time is not disturbed. Einstein's idea, let's say, and eventually, supported by math, etc., was quite different. The theory of general relativity that he put forward suggests that actually the presence of mass, even without any motion, disturbs space and time. Now, we're going to forget about time. Okay, it's hard to think about it. We're going to think about space only, and we're going to think about two-dimensional space, so a sheet, a fabric. Okay? So if I just place two masses on an undisturbed or close to an undisturbed flat sheet, it's going to get disturbed. And it's going to change the distances between points in their vicinity, and it's going to create dimples. If I now give the velocity a kick in one of them, then the motion is following the curvature of that space. That's one way to think about it. So the motion now is not because they're connected instantaneously. The motion is in response to the physical environment of the space-time. Okay? Think what else swirls following the shape. You can think a few things in our everyday life. I won't mention one of them. Maybe not very appetizing. Okay, so now if I give a kick, you start getting disturbances because of the motion. The dimples start getting disturbed, so you generate waves, and waves propagate just like light waves, just like electromagnetic waves, like the waves that come out from any light bulb, okay? So gravitational waves are basically oscillations of space and time, forget time. So the space disturbance goes up and down. When we say we detected the gravitational waves, we mean we detected disturbances in the space around us, okay? Because a gravitational wave was passing through. Now, these waves, it can be proven, it was proven by Einstein that travel at the speed of light, and they carry energy. Every wave in nature carries energy. Otherwise, it can't propagate, okay? So the oscillation needs force to create, to disturb whatever it's disturbing, and that takes energy, okay? All right. So I'm gonna stop here for a minute and take any urgent questions. We'll have time for questions later. Okay. All right. Now, I'm going to ask the question, did we know about black holes before LIGO? What's the big deal if we knew already? Well, we knew about black holes in electromagnetic astronomy, and we knew them in X-ray astrophysics. In fact, I was studying them before I got into gravitational waves. And the way we knew them is because black holes can exist in binary systems with companions, partners that are regular stars, like our sun or more massive than our sun. But when black holes are in this kind of situation, they can pull material from their companion. Material falls into the dimple of the black hole. It gets really hot, the gas, and it emits thermal emission, like a hot light bulb, but so hot that the emission is in X-rays. Okay? And through analysis of the X-rays, we had concluded in the 70s, so post-Einstein, that at the center of these disks, there was a dark object, and we could argue, I'm not going to go into the details, that there was a black hole there. Next question, did we know about neutron stars? Yes, we did, from electromagnetic astronomy. This, by the way, is Chicago, the Chicago skyline from Lake Michigan, from the Adler Planetarium. And this is the edge of a neutron star to scale if it were hanging above Chicago. A little ominous. But that's the size. They're tiny. So how did we know about them? Again, without going into the details, they were discovered in the late 60s by Jocelyn Bell Burnell, and they were discovered in radio waves, the other side of the electromagnetic spectrum. And they were discovered as radio lighthouses for reasons that I'm not going to go into now. Neutron stars have magnetic fields, and they can launch radio jets. And if that, just like a lighthouse at harbors, if that radio beam, instead of optical beam, crosses our line of sight, we get radio signals, and that's how they were detected. And through analysis, we concluded they must be neutron stars. So we knew black holes existed. We knew neutron stars existed. In addition to that, we knew that neutron stars existed in pairs. Because later, student and advisor, using a radio telescope that doesn't exist anymore, detected a pulsar in orbit around another neutron star. So now we knew not only compact objects exist, but they exist in pairs with other compact objects, at least neutron stars. And people could apply Einstein's theory of general relativity and gravitational wave analysis and conclude those neutron stars can merge on the lifetime of the universe. So then the interest about, and of course, we knew gravitational waves must be emitted. So the interest to detect gravitational waves got heat up. This was mid-70s, early 70s. So that was the motivation. With the first discovery, the two black holes, what we didn't know is that black holes of that kind of mass existed, that black holes existed in pairs. We were suspecting, but had no proof. And then we had no way of detecting gravitational waves because it was super difficult. Okay, how do you detect something you've never detected before? You have to ask the question, what does it do? What does it do to my environment, the thing I'm trying to detect? You have to think about its influence and then say, okay, that influence, I have to build an instrument that can measure that influence, okay? So that's how you start. Now, what gravitational waves do is they disturb space, and they create an oscillation. The oscillation has a very particular form. We call it the quadrupole form. And it disturbs distances, remember, between points. That is, the fractional disturbance of the distance between points is proportional or equal to half of a quantity that we call gravitational wave strain, the strength of the wave. But this thing has no dimensions. It's the difference of the distance in points divided by the original undisturbed distance. When I said gravitational wave measurement was 1 part in 10 to the 21, What I meant was that what we measured was the delta x was 1, and the x was 10 to the 21. Tiny. Okay. I suspect I have to accelerate, even without looking at the clock. So I'll tell you that if a gravitational wave is propagating perpendicular to this screen, then the undisturbed points on the plane of the screen are going to start oscillating this way, except it's not going to be that enormous oscillation, but it's going to be tiny. The waves are extremely weak, so now how do you detect them? They're so weak that it's like trying to detect a change of the size of the Earth, a change that the size of the Earth is changing by the size of a proton. That kind of measurement. How can you tell the whole size of the Earth is changing by a tiny little proton length? So the core idea lies with laser interferometry. Sorry, I want to stop the video. And now you can start thinking, you know, at the end, it took 40 years. The idea was put forward by scientists across the world, but it was really articulated in a practical way and doable way by Ray Weiss and Ron Driver in some collaboration, but Ray Weiss first. You couldn't do this. It took 40 years, but you couldn't even come up with the idea if you didn't know what laser is, what interferometry is. Okay, so Einstein's theory, 1916. Laser interferometry, early 70s. Black hole discoveries, late 60s, early 70s. Neutron stars, the same. So you see why it takes so long. Okay? One thing depends on the other. That's how science and engineering go hand in hand and lead to progress. Okay, so the L-shape telescopes I showed you is because this is what happens inside them. A laser gets split and goes down the two L-shaped vacuum tubes, bounces off two mirrors there. The lasers come back together, and we look at them in an interferometry pattern. The laser design is such that if there is no disturbance, the two lasers come back. The mirrors are set in such a way that the two lasers come back, and they cancel each other. You get zero light when you try to do this detection. I'm going to give you another. So if there is no wave, you get zero light. If there is a wave, you start getting this disturbance, wave motion I showed you, and then you get light, non-light, light, non-light, light, non-light. So that's how the measurement is done. I'm oversimplifying. I am being so unfair to our instrumentation scientists, physicists, laser physicists, and engineers. But that's the physical principle. All right. And our three colleagues, I mentioned two of them earlier, got the Nobel, who were instrumental for eventually convincing the community to pursue this, got the Nobel Prize in 2017 after the first discovery. All right. So these are the first gravitational wave telescopes. Now I want to give you a sense of how small is 1 part to the 10 to 21. The fractional, I told you, delta x over x, 10 to minus 21. But these tubes here have a finite length. They are 4 kilometers long. So when they're 4 kilometers long, then the delta x is 10 to the minus 18 meters. So I'm going to give you a sense of what is that little change. I told you, compared to the Earth, it's like wanting to measure a proton at the edge of the Earth. Okay, so take 1 meter, about 3 feet. 3 feet. I don't know if this looks like 3 feet to you. Does it? You take 1 meter. Now I need my glasses. you divide it by 10,000, you get the thickness of one human hair, the thickness. You divide by 100, you get the typical wavelength of optical light. You divide by 10,000, you get the typical diameter of an atom, hydrogen atom, any atom, almost any atom. Then you have to divide again by 100,000, you get the size of a nucleus. You're still not there. Then you have to divide another factor of 1,000 to get to 10 to the minus 18. That's the measurement. No wonder people made fun of the original proponents. Who could imagine one can measure this? All right, so now we're going to go back to the time of the first discovery, and this time I will ask for some sense of time. Oh, it's up there. Thank you. I don't need it. We're good, actually. So this is, I showed you. It stopped. This is what we detected on September 14, 2015 in our data. The way we collect our data is basically a time series of the sort of relative position of the mirrors. Again, I'm oversimplifying. But what we saw between the two detectors, Hanford, Washington, Livingston, Louisiana, if we shifted them by 7 milliseconds, which is the speed of light travel time between the two locations, they aligned, and what we saw is garbage in the beginning, that's noise, and then a pattern revealed itself, perfectly aligned pattern that looked like our simulations. The peaks, higher and higher, waves stronger and stronger, the distance between the peaks, smaller and smaller, the frequency increasing. That's the telltale signature of the gravitational wave we were looking for. And another way to plot it is frequency as a function of time. This is gravitational wave strain, strength of the wave, as a function of time. And look at it. The peak is at 1 times 10 to the minus 21. That's exactly what we measured. Frequency as a function of time, and what you get is a little banana, because the frequency is increasing as a function of time. That first signal lasted for 0.6 seconds, so about half a second in our data. That half a second changed our lives. First, it changed our lives inside the collaboration. Eventually, it changed science and engineering as a whole. The sound, two reasons. I would like to explain this. One is silly and coincidental. The frequencies that the LIGO detectors and Virgo are sensitive to, different detectors are sensitive to different frequencies. Radio telescopes in radio, X-ray in X-rays, regular telescopes in optical. LIGO is sensitive to, especially at that time, 100 to 200, roughly, now wider. Those frequencies are very similar to the frequencies of sound, not gravitational waves, that our ear is sensitive to. Who knows what's the frequency of A? Exactly, 440. So, hertz. So you can take the gravitational wave frequency, convert it into sound with the same frequency, and play a sound. And that's the sound you listen to. Okay? That's a coincidence, and it has no physical meaning. However, the gravitational wave detectors act like ears, and that is not a coincidence or a silly fact. Telescopes are pointing instruments, like our eyes. I can see you, I cannot see at the back of my head and behind me. Our ears function differently. We can hear noises from all over us, all around us, up, down, behind. So gravitational wave detectors, that L-shaped thing, can listen to gravitational wave signals from all around, okay? It's not like a pointing telescope. So that's why we often make the analogy with sound, not just the silly coincidence. Okay, so this particular collision had certain characteristics that at the time we all remembered with love and shivering, but now it's kind of vanilla. Most of the binary black holes that we have detected are of this type, about twice, 30 times the mass of the sun. They're typically billions of light years away, and then they travel for billions of years to reach our detectors. The waves, not the black holes. They have tremendous energy. They carry tremendous energy, catastrophic energy, dangerous energy. If that energy would interact with us and get deposited in us, but it doesn't. We're transparent. Gravitational waves go through matter like nothing. In fact, Steven Weinberg looked into this question towards the end of his life, the interaction of gravitational waves with matter, and concluded it's negligible. So very bright, but we don't feel that energy. It doesn't affect us. It doesn't hurt us. And that's why they're hard to detect. All right, so that's the opening of our field in 2016. I will say that astronomy, you cannot do astronomy with one event, okay? Imagine if all we knew about the universe was the sun and no other star. Imagine if all we knew about our universe was one galaxy. We wouldn't know anything about the Big Bang, all the things Steven Weinberg studied. You cannot do astronomy. You can't say we opened the field, you can say, but you cannot say we now do gravitational wave astrophysics if all you have done is detected one source. So it's really important that now we're seeing a few binary black hole mergers every week, and we have hundreds of them. So now, but I'm talking to you in detail about the first one, and I'm using it to explain how it was done. I should have said that all of this work, I realized I didn't make it explicit. I said many of my colleagues here at the university are part of the same collaboration. This collaboration I speak of, the LIGO scientific collaboration, includes hundreds of people, okay? Almost 1,000. This is what you call big science. You cannot do things like this with a team of 10. All right, so next I want to tell you about a subfield, the dawn of multi-messenger astronomy with gravitational waves. We're going to hear another little chirp. I didn't say it before. The banana as a function of time, whoop. This is longer. Where are you? I don't know what happened. I don't want you. I don't know where the sound went, but you heard it. Okay, I didn't do this on purpose. It's longer. That, when we got that signal on August 17, 2017, by then we were experienced gravitational wave observers. We knew these were not black holes. The length told us immediately This longer signal is coming from lower mass objects, and lower mass objects, knowing astrophysics, not immediately to you, but meant neutron stars. So we knew now we have the next class of collisions, cosmic collisions. In addition to that, within 2 seconds, it's a little complicated story, but I'll simplify. Within 2 seconds, we also had a gamma ray signal from the same part of the sky. Hence, multi-messenger. A gamma ray signal that we had seen 1,000 times before. A gamma ray signal that we call short gamma ray burst that we had seen since the 70s and was hypothesized for decades, for 40 years, that neutron star collisions probably produce gamma ray bursts. But we didn't have a proof, only theory. And lo and behold, the first time we detected in gravitational waves something that we could prove it was a collision of 2 neutron stars, we also got the short gamma ray burst. And that was proof for the mystery of what produces short gamma ray bursts. So very quickly, this is what we saw. This is the long whoop. And I'm only showing you here about 30 seconds, but it lasted 160 seconds in our data. And the gamma ray signal here. This is where the gravitational wave signal ended, and a little later, the gamma rays came. Why? Oh, by the way, between the gamma rays and the gravitational waves, we could tell where on the sky it was. And the optical astronomers went crazy, literally. Every single telescope, no matter the size of the telescope on the planet, went and looked at that part of the sky. And what we discovered, we, the royal we, I did none of this work, or my group, in terms of the electromagnetic observations. What we discovered is that in the galaxy of that burst and gravitational wave source, there was an optical source that initially was bluish, the 17th, and 4 days later was reddish. And that was a telltale signature of another expectation from theory, that when neutron stars collide, they don't just give you gravitational waves, they don't just give you short gamma ray bursts, but also they produce very rare elements. The elements that actually are gold and platinum and all those heavy elements that are precious to us. Why are they precious? They're rare. Why are they rare? Because they happen in rare events, but also because we cannot produce them in the lab. We can't make them, we have to mine them. And they're not in high quantity. And hence, they're precious. So this double neutron star, the source that couldn't stop giving, solved so many mysteries. One source. I said, you cannot do astrophysics with one source. Boy, this source did astrophysics for us. All right, so this is another movie that simulates 2 neutron stars coming together. The black hole collision I showed you was an actual scientific movie of actual event horizons. That's a word I haven't used yet, and I won't explain it, but 2 black holes actually being simulated with Einstein's equations, etc. This movie of 2 neutron stars coming together and eventually colliding, this is an artist's impression from NASA. So it's gorgeous, and if I had the sound on, you would hear some really fancy music about this collision. So 2 neutron stars emitting gravitational waves, coming together, forming a single object at the end of the collision, and at the collision, now creating a whole spectrum, a firework of electromagnetic emission. And the gamma rays come out, now that we understand the physics, come out in the jets, and the blue and red emission comes out in this spherical cloud at the center of the collision. This is where all the gold and platinum is. 1/10 of the mass of the Earth, if only we could mine it there. All right. So these two discoveries, one in 2016 announced, one in 2017, were declared as the breakthroughs of the year across all of science and engineering, back to back. Where are we now? This is where we are now. We're in the butterfly era, okay? And what we're trying to understand is, how do these pairs of black holes form? Why do we have so many? Why are they more massive than what we see in the X-rays? Why do we have fewer neutron stars? Why is there some kind of a gap in here? Why don't we see more black holes beyond 200 solar masses? There are some answers, but we have more questions. So we expect hundreds and hundreds of gravitational wave mergers, and we're looking into the future with new facilities that, if built, remember astronomy, we have tons of telescopes, right? Progress over centuries of electromagnetic astronomy. This is a 10-year field. So we're looking into new facilities that will probably take 20 years from now, 30 years from now. We're looking at the next century, okay, the rest of our century. For me, it's the next. I'm still in the previous century. And what we would be looking at with these Cosmic Explorer and Einstein telescope in Europe and in the US, if built, we're looking at millions of binary black hole mergers, like millions of galaxies that we detect now, and we're learning so much. So I know I did go over. I will leave you with that thought, and I'm happy to take questions. Thank you.
Okay, but before we have some questions, I hope everybody got a sense for Dr. Kalogera's work studying gravitational waves. It's clearly expanded humanity's understanding of the universe, and there's just more and more to come. By sharing her knowledge, she really honors the legacy of Steve Weinberg, a dedicated teacher to all, from his students to the wider public. And the University of Texas at Austin would like to commemorate tonight's lecture by presenting her with the Steven Weinberg Memorial Lecture Medal, which I have not lost.
Oh, wow.
Here you go.
Okay.
And you get to awkwardly wear it for us.
Okay, thank you. Wow. Oh my God, thank you.
And now, I'm sure she's happy to take some questions. Oh, we have to take a picture.
Maybe together.
Yeah.
Thank you.
All right, so I'm sure she's happy to take some questions, and apparently Deirdre Shoemaker has agreed to moderate or find people in the audience. I don't know if we have a microphone or not, but.
Yes, we have a mic.
You guys just want to make me run around. Oh, you're going to run even better. Man on that first. Sorry. Wait for the microphone if you don't mind.
That will help everybody online. So.
Yes, please do.
So my intuition is blown. I think of neutron collisions like supernova, a rare event. We don't see that many of them. Yet you're telling me we're having 10 to the 6 detectable events is in your plans, right there. Mm-hmm. That's a totally mind-blowing thought.
Yes.
That these violent events are out there.
Yes.
Yes. Why was this not hypothesized before? This is very confusing to me.
Yeah.
Because we went to find this very slowly. If we knew there were millions of events, surely we would have done this faster.
Okay. So early on, when I started working on gravitational waves, I was in the business of predictions. before I started doing data analysis with my group. So actually, we did predict we made all kinds of predictions based on the best understanding of astrophysics we had about the formation, about how stars die, and how black holes formed. But we had such little guidance from observations before the first discovery and so incomplete understanding for how stars evolve through all kinds of different stages until they might get to have a pair of black holes. That our simulations, within all our uncertainties, they were predicting anywhere between there are 0 binary black hole mergers in the universe, 0. We had astrophysical arguments for why binary black holes can form, but too far apart from one another that the gravitational waves would never be strong enough to bring them to a merger within the lifetime of our universe. So 0 detections, all the way to millions of detections. And so you couldn't make a fuss about it. With the double neutron stars, because we had the radio pulsar detections with a neutron star to them, there was a floor. We at least knew these things exist as pairs, and they will merge within the lifetime of the universe. So there was at least a minimum merger rate we could predict from the radio astronomy side. But that rate was relatively small, and the reach of our detectors that we were dreaming of was not big enough. So these are rare events. So if you can only see, detect, listen to double neutron star mergers out to, let's say, Andromeda initially, or a little farther away, maybe you're gonna, again, we had uncertainties, maybe you'll see 0, maybe you'll see 3, and we didn't know. We knew there was a minimum rate, but we couldn't cover a big enough volume of the universe to have certainty that our detectors are going to see something or are going to listen to something. Now, when we got the first binary black hole detection, with methods my group had developed from radio pulsars, we were able to calculate the floor for binary black hole collisions, same as with the double neutron stars. And then the 0 detection scenario got excluded. But then again, we were in the same situation. With one event, the rate is not very well constrained. So again, big uncertainties. But our detectors back then, 2015, could only see up to so far. So the volume coverage for rare events, too little. Now we have, because we have 200 events, the rate constraints, much better. We know the rate, measured, not astrophysical simulations. And these detectors are of technology that if we achieve it, we're going to be able to cover, when it comes to black holes that are massive, we're going to be able to cover, this is what shows you, this detector could see a 30 plus 30 solar mass binary black hole merger all the way out to almost a redshift of 100, which basically means before stars were formed. That means a detector like this will see every single binary black hole merger ever in the universe. And that's how we get 2 millions.
We don't need LISA then.
LISA, it's a different, may I answer? This is like a separate question. LISA is very important. We do need LISA. I'll tell you why. LISA is not a more sensitive LIGO. LISA is detecting in a different frequency band. So Hubble sees optical light. It could never have detected X-ray binaries and the black hole in X-ray binaries. So Lisa sees completely different types of gravitational waves. Lisa will discover gravitational waves from white dwarfs. And Lisa will discover gravitational waves from supermassive black holes, millions and billions. Well, billions no, because that's even lower frequency. But millions and tens of millions supermassive black holes merging in the centers of galaxies, when galaxies merge. But it will not see the kinds of collisions LIGO sees. So X-ray telescopes cannot see optical light. Lisa cannot hear LIGO music. Okay?
More questions?
Do you think it would be possible using gravity wave observations to see beyond the cosmic microwave background?
Yeah, so there are definitely predictions about gravitational wave emission from the very early universe, from the birth of the universe. There are many different theories about how strong that emission would be, what characteristics it will have. In practice, even with all the uncertainty and all the predictions, we do not expect that the LIGO detectors will really probe that kind of emission. Very extreme models predict very strong emission from the early universe, but they're very extreme models, very optimistic, let's call them. However, this detector that we envision for the coming, I would say, 10 to 20 years, a big part of that science will be a background, like the cosmic microwave background is all over us, a background of gravitational waves, potentially from the early universe.
Hi, thank you. I have a bit of an elementary question. From my understanding, gravitational waves cause a change in the space-time metric, right? Mm-hmm. Which would affect space distances in time dilation as well. Mm-hmm. So couldn't we use atomic clocks to sort of detect waves?
Yeah. This is not a simple question or simplistic or whatever you called it and I didn't catch it. This is a very interesting question. There is research literature on how to use atomic clocks to detect gravitational waves. I think there's literature for how to put atomic clocks on the moon, possibly. So people are thinking about it. It's conceptual basis. I'm not an expert in that, I will say. I have read a couple of papers. It seems to me that it's conceptual. It's possible in principle, but I believe with the accuracy of the atomic clocks right now and the kinds of sensitivities we would see in the time oscillations, we're not there yet from a sensitivity perspective. But certainly it's being discussed in the research community.
Thank you.
Great question.
We have a question online, and then we'll take this.
This question is, hi, I'm a PhD student working in dark matter phenomenology. I was wondering whether the presence of accumulated dark matter in neutron star binaries could alter the gravitational wave signal sufficiently to serve as a probe for dark matter detection.
Yeah. The short answer is no. The longer answer is no, because there is the gravitational potential around neutron stars is not deep enough, it's not like a galaxy, to retain any dark matter of significant mass. And the gravitational wave signatures respond to how much mass you have dancing around, okay? So if there is any dark matter, it is inconsequential, let's say. Anybody disagrees with me from my expert colleagues? Paul?
Well, a variation of the question. The pulsar timing arrays have the potential to detect a scalar field dark matter.
Yes.
If there is a proper sort of matching of the frequency of the period and the wavelength that would correspond to that.
Yes, I didn't think of going in that direction, but now, Paul, you got a question, you're answering the question you would like have asked, but but I don't disagree with you. Yes, there is a potential, yes, yeah.
Hi. By what mechanism is the mass of the merging black holes converted into the energy of the gravitational waves?
By what? Restate this. By what way?
How is the mass of the black holes converted into the energy of the gravitational waves?
Yeah.
Because you stated that those carry enormous energy.
So when you're still, and again, now I'm going to look at my expert colleagues, because that's not my expert, but I'll give you the answer. So when you're still in the in-spiral phase, and the two black holes are far away from one another, you're not altering the mass, okay? You're just cooking up, I'm sorry, I'm being casual. You're just disturbing the space-time, and you're taking energy away from the orbital motion, not from the mass of the black hole. When the two black holes come together and they have a peanut-shaped-like common envelope, the event horizon, the imaginary surface from which even light cannot escape, now that surface basically is a measure of the mass of the future black hole that is about to form. And that disturbed object, which is not yet a classic black hole, is shedding gravitational waves at a much higher rate because of its gross asymmetry. And it is then where you're removing gravitational waves no longer from the orbit. There's no orbit, they're now together. But you're removing it from the actual combined mass of this the peanut-shaped black hole-like object, okay? So that's when you start losing actual mass, converted into energy in gravitational waves that are moving away. Would you describe it in any different way?
You got a nod from Deirdre.
Thank you, dear.
I had two questions, but when the gentleman asked about Lisa, that took away one of my questions.
Okay.
You haven't referred to possible collisions between neutron stars and black holes.
Yes,
Okay?
correct.
So whatever you might say about that would be welcome.
Yeah.
And with regard to Lisa, so it's not on your chart with regard to future instrumentation.
Yeah.
Is Lisa unlikely or likely to be a part of the future?
Yeah.
Likely.
Yes. So this is heavy. Glasses. And let me answer the first by going back to our butterfly. It's close by. All right. We have detected mergers of neutron stars and black holes. And they're not insignificant. I just had to, so thank you for asking. And they are a few. And their rate is the merger rate astrophysically, not the detection rate, no, not the number of sources, but the rate for how often they happen in the universe is somewhere in between the double neutron star rate merger and the binary black hole rate within the uncertainties. And they're here. I'm going to try and find one that is clear. Do we have one? Yeah, this one. Here's an orange dot well into the regime of masses that are neutron stars, so like 1.5 solar mass, combined with a blue dot that is more than 5 solar masses, giving us another black hole. So that's a clean neutron star black hole merger. Okay, there's a couple more, and then there are some systems that are, we don't know, like maybe neutron star, mystery object, black hole. Okay. But we have, I don't remember now, we have Aaron. Where is Aaron, or seeing you? Do you remember how many black hole neutrons? 3? 4. Okay, I got it off by 1. Second question. LISA, yes, it's well on its way. It's really being built by Europe. We had a chance to be real 50-50 partners for political reasons a long time ago. We missed that chance. Now we have a small contribution, but it's going to happen. Launch date 32? 36. When it becomes 36, and I want to show you this, which is the the gravitational wave spectrum. LIGO is here. This is frequencies. Well, this is frequencies. So 100 hertz here, dead in the center of LIGO, Virgo. This is what we've been observing, okay? And then LISA is here, 10 millihertz and 0.1 millihertz, okay? This is where LISA is going to see very different types of sources. But yes, it's being built, and it's going to be a space mission. Okay?
All right. In lieu of time, I think it'd be great if we could all thank Dr. Kalogera again for a good talk.
Thank you for coming. And thank you again.